So here's a brief outline of my talk. I will give you some introduction into electron-molecule interactions and what kind of processes that we can do using our software. And at the end, I will entertain you with some results that I obtained using our software. So electron-driven processes and for calculating cross-section for those processes are really important in many applications. One of the major applications is in plasma technologies, where these big semiconductor and electronic companies, they love this kind of data in plasma etching, sputtering, like that. And recently we did a project, very cool project, that where we calculate cross-section for electric propulsion system. So I thought that's kind of cool. And not only in plasma applications, the electron-molecule scattering, that phenomena is really important in other applications, such as radiation biology and astrophysics. For example, in radiation biology, you encounter this low energy electron interacting with the DNA and breaking the strand. Typically, biological molecules are very big compared to our common molecules that we encounter in plasma application, but this is one of our potential future applications in our software. And if you don't love the data, then you can do this calculation for the love of physics. So it involves a lot of quantum mechanics and quantum chemistry. So what we can do with our software, given a molecule, we can calculate a range of cross-sections, which we can divide into two processes, which is elastic scattering and the inelastic scattering. So here I made a sketch of what kind of inelastic processes that we can treat using QVC. I think Matt gave a nice summary of this at the end. So you have the incoming electron, it's the molecule, and it goes to a sort of negative ion resonance. And then you can treat you can see vibrational excitation, rotational excitation can happen, dissociative electron attachment or dissociative ionization. So we can calculate the cross-section for all this. So there are many methods that you can use to obtain the cross-section, but if you are a quantum chemist or a quantum physicist, you know how hard it is to solve this problem theoretically. Like for example, if the molecule is bigger, you can never do that exactly. So in our software, we use this method called R-matrix method, which is based on a couple of approximations. The other methods, they are not developed to a level that they can treat bigger molecules, but our matrix method can treat bigger molecules. So essentially, or in brief, what we do here is we divide the interaction space into two, the outer region and in the inner region, and we treat these two regions separately. So the inner region encapsulate the molecule. I remember Matt showed this window at the end of his presentation where you see a big sphere and inside you saw the molecule. So this is that sphere. And in this, and the inside of this, we consider electron exchange interaction, electron repulsive interaction. And we solve a Schrödinger equation, which looks like this. And this Schrödinger equation takes in all the electrons in the molecule and the alien electron or the incoming electron. And we solve this equation using an expansion. And in the expansion, we include the target wave function. And this process, the input for this process is taken from mol-pro integration. So giving a sort of ab initio nature into our calculations. The outer region, so now let's look at the outer region. Here we ignore all the interaction that we treated inside this sphere. So we only consider all this long range interaction like dipolar, Coulombic, and we do a single center expansion of the wave function, which looks like this. And here, if you look at this, F is the scattering radial wave function that the outgoing electron has. And we solve this using the initial condition that we obtain from the solution from the inside region. So on the surface, the solution looks like this, which has the data from the R matrix, here R, and it is constructed from the solution inside. And then we propagate this solution to an faraway region and calculate phase shift or the eigenphases that Matt mentioned earlier. And from then, we calculate the cross sections. But before I go into my result, let me go a little bit deeper into what happens when the incoming electron interacts with the electrons of the molecule. So to have some good understanding. Here I picked an example. Let's take the oxygen molecule. So it has 16 electrons, and they are distributed amongst the molecular orbital with these occupancies and geometry. So we can visualize in a 3D space how they are distributed. Okay, what happens? All right. So in our calculation, in addition to this ground state electron distribution, we introduce virtual orbitals and the continuum orbitals. Now, these are all electrons which belongs to the molecule. So now what happens when the incoming electrons interact with the molecule? So when the incoming electrons occupies virtual orbitals, and that scattering model, that scenario is called the static exchange. And if you look at the incoming electron occupies a virtual orbital, and probably one of these electron at the home orbital jumps into a virtual orbital, and that's called the static exchange and polarization. And the next step, the next scattering model is the configuration interaction or the close coupling method. I remember Matt mentioned about this. If you want to do electronic excitation calculations, so this is the scattering model that we should pick. In this model, a bunch of electrons can jump onto virtual orbitals. So that will essentially increase the total number of states that you consider in your calculation. For a small molecule, of course, you can loosen up all the electrons in the ground state, but if the molecule is bigger, and if you try to do that, then your computer will cry because it will take a lot of computation. I mean, it will become computationally expensive. Okay, finally, now let me show you some results that I obtained using QEC. So here is a graph for showing the elastic scattering cross-section for methane molecule. And here I compare the result from QEC and with the experiment. You can see a very nice agreement. And also we obtain the famous Ramsau 1000 minimum for the elastic scattering for methane. So here another example for CH3F, where I show the differential scattering cross-section and the total elastic scattering cross-section. So you can see a very good agreement with the experimental and our theoretical calculations. So finally, the vibrational excitation of water molecule, that from the last example that Matt chose. So here I play with the scattering models and compare with the available experimental or the recommended data. So this is one of the good things with QEC, where you can choose the scattering model, choose how many number of electrons contribute to your cross section. So you can do this using a few clicks. That's very nice. And so here, if you look at the So in this panel, I calculate the cross-section for symmetric stretching and antisymmetric stretching vibrational excitation of water molecule, and this is the bending mode excitation. And the overall, the static exchange and polarization method agrees. And you can extract what kind of physics happening when you look at all this cross-section data. So in conclusion, as Matt emphasized at the end, QEC is really user-friendly software that you can use to calculate electron-molecular scattering cross-sections. And it's like having yourself a postdoc who does all this coding, all these calculations by hand for yourself. So with this MolPro integration, you can easily introduce an ab initio level of calculations into your problem. And in the future, we are trying to integrate Gaussian into QEC so that you can have larger range of access. So yeah, I think this is the end of my talk. And if you have any questions, I would like to answer.